Hello and welcome to the Statistics and Mathematics Tutors course on stochastic processes. So in today's video, we are going to continue our lesson on queuing theory by working some examples. So stay tuned and let's get into the video. The first question says that arrivals at a telephone booth are considered to be Poisson at an average time of 8 minutes between one arrival and the next. The length of the phone call is distributed exponentially with a mean of 4 minutes. Okay, good. So now we are giving a queuing theory question. The first is to note down your arrival rate and the service rate, followed by the right performance characteristic the question is demanding for. As in, is it LS, LQ, WQ, or whatsoever? That's the next important thing. Once you get the formula right, it means you are almost there, right, of getting it right. So let's first fetch the performance characteristics. That is the parameters, the mu and then the lambda. So we are giving 8 minutes between one arrival and the next. This is the inter-arrival rate. You get it? This is not the arrival rate itself. That's not lambda. But they're not telling us that the inter-arrival, there's 8 minutes between one arrival and the next. So how do we know the right lambda or the arrival rate? We know that the inter-arrival rate is given as 1 over lambda. You get it? So if 1 over lambda is equal to 8 minutes, it means that lambda should be equal to 1 over 8. You get? So we get lambda to be 1 over 8 per minute. Take note. Yes, per minute. So if you want this to be converted to hours, the arrival rate per every hour, then we're going to multiply this by 60. Alright? Good. So we do the same thing for the service rate. We said the mean of the exponential distribution is given by 1 over mu, which is the inter-service rate. Okay? So that also gives us 1 over mu to be equal to 4 minutes. Okay? Yeah, so we get mu to be 1 over 4 per minute, which is 0.25. Okay? Yeah, so the next thing is to move on to solve the real questions. The first one wants us to determine the fraction of the day that the phone will be in use. Okay? This is rho. In rho, we all know that's the fraction at where the system is busy. How busy the system is rho, and is given by lambda over mu. Okay, we know lambda already, and we've calculated for mu as well. So we divide the two. By doing so, our utilization factor becomes 0.5. We move on to look at the next question. They want us to determine the expected number of units in the queue. Whenever we talk about expected number, the notation is usually the else. Either it's going to be LS or LQ. But we are talking about Q here, so that will be LQ. So our next performance characteristic is going to be LQ, and that will give us rho squared divided by 1 minus rho, and we get 0.5 as our answer. The next is the expected number of units in the system. Expected number of units in the system. That's the opposite for that of the system. So that's going to be rho all over 1 minus rho, and we get 1. Right? Yes, we move on to the next. So these are very simple. Once you know the formula and your parameters, just fix in and get your answer, then we good. We don't need to spend much time here. So the expected waiting time in the system. So expected waiting time, that is W. Okay, but which of the W's is it going to be? Is it WS or WQ? It's WS because it's system. So that's WS. So WS is given by 1 over mu minus lambda. Okay, 1 over mu minus lambda. So we get 8 minutes. Okay, good. Yes, so let's look at the probability of no queue. When they talk about no queue, most students think no queue, probability of no queue is going to be P naught. Okay, yes, you are not far from wrong and not right too as well, because one person cannot form a queue. So if they say no queue, that's going to be what? Either like one person, because if you are a single individual in the unit or in the system, you are just going to proceed to service. Do you understand? So one person cannot form a queue. So no queue means P1 plus P naught or P naught plus P1. Simple as that. Okay, so we calculate the 2, P naught plus P1, and we get 0.75. Okay, the next is for us to determine the probability that an arrival will have to wait in queue for service. Alright, an arrival will have to wait in queue for service. So if you have to wait in a queue for service, it means that the system is busy. You understand? And that's still rho. That's lambda over mu. So that is simply the answer. The next is probability that exactly 3 units are in the system. So this is P3. Okay, this is P3, and P3 is going to be rho. That's going to be rho to the power 3 times 1 minus rho. Okay, remember we said Pn should be equal to 1 minus rho times P to the power n. So P3 will be 1 minus rho times P times rho to the power 3. Yeah. So we get 0.0625 as our probability. So we look at the next. That's to calculate the probability that an arrival will not have to wait in queue for service. An arrival will not have to wait in queue for service. If you will not have to wait in queue for service, it means that the queue is actually empty and you are the person going to fill it up. So you don't need to form a queue, you just have to proceed to the service center. So in other words, that's P naught. Okay, P naught is 1 minus rho. We know that already. That's 0.5. The next is for us to determine the probability that there are 3 or more units in the system. 3 or more units in the system. So that's I. Let's look at I. 3 or more units in the system. So that is summing from n equal to 3 to infinity. That's 3 or more. So this can also be seen as 1 minus, that's 1 minus at least 2, because the complement, right? The complement will be 1 minus P naught plus P1 plus P2. That will still give you the same answer as 0.125. Okay, let's look at J. So this is probability that an arrival will have to wait more than 6 minutes in queue for service. Okay, so let's look at the right formula. That is rho times e to the power negative mu minus lambda times t, where t is the time. Remember, we calculated our mu and then lambda in terms of per minute. Okay, is per minute. So meaning we're going to multiply this by just 6. We multiply by 6, not 6 over 60, because our parameters were calculated per minute. Okay, and we get 0.23618 as our probability. Okay, we look at the next probability that more than 5 units are in the system. You get it? More than 5 units are in the system. So this is similar to the I. Okay, just that this one has just that's at least 5. No, at least 4, right? No. So this one will be at least 6, because more than 5 meaning 5 or like 6 or more, right? So we sum from 6 to infinity. Okay, or we can simply take the complement. That is going to be 1 minus P naught minus P1 minus P2 minus P3 minus P4 minus P5. That can also give us the answer, right? Good. That can give us the answer. So if we come here, that will simply give us rho to the power 6. Okay, rho to the power 6, and we're good with that. The answer will be 0.015625. Alright, good. So let's look at the next one. We have to calculate the probability that an arrival will have to wait more than 8 minutes in the system, right? So you can see that this is similar to one of our questions where we have probability that an arrival will have to wait more than 6 minutes in queue. So this is in the system. So yeah, let's look at the difference. The difference is just going to be the rho that's attached to the formula. So you can see that this one has no rho. The system has no rho, but that of the queue, yeah, the queue has a rho attached to its formula. You can see here, that's our J. That's rho times e to the power negative mu minus lambda times t. So the latter one had no rho attached here, right? Good. So by doing the correct calculations, we get 0.367879 as our probability. Okay, let's look at the last question. We have to determine the expected waiting time in the queue. Okay, yes, so that's the W's, but this particular one is in the queue, so it's WQ. All right, yeah, so WQ can be calculated simply by taking W, that's LQ, divided by lambda, so that would be 0.5, which was our LQ. We divided by our lambda, which is 0.125, and get 4 minutes. Okay, good. So this is our first question. Let's quickly look at the second one. Our second question. Good. So at a stamp vendor window of a post office, 20 customers arrive on an average every 10 minutes. So every 10 minutes we have an arrival. Good. If every 10 minutes there's an arrival, so how many in a minute, how many people are we going to expect? Do you get it? Yeah, in a minute. So 20 customers will be equal to 10 minutes. So lambda customers per minute should be equal to 60 minutes. That's an hour. So by doing, we can calculate for our lambda per hour, or we can look at the per minute. All right, so the per minute, if you do correct calculations, we are going to get 2 customers per minute. So it means per hour we are going to have 2 times 60, that's 120 customers per hour. Right, good. So same goes for the service rate. The vendor clerk can serve 5 customers in 2 minutes. So if in 2 minutes 5 customers are being served, it means per minute is just going to be like half of this number. That's 5 divided by 2, and that will give us 2.5. Okay, let's move to the main questions. So we have to determine first the average number of customers in the system. Average number. So whenever you hear number, that's the L's. Okay, but this particular one is in the system, so that's LS, and LS is given by row divided by 1 minus row. Okay, good. So by doing so, we get 4. Yeah, 4 customers on average. Let's look at the second one. So we are to determine as well the average waiting time of a customer in the queue. So that's the W, but this particular one is WQ because it's the queue. WQ, alright? Good. So WQ is going to be LQ. Okay? LQ divided by lambda. So LQ is 3.2. We divide it, then we end up with 1.6 minutes. Alright? Good. That's the last but one question. Probability that we determine the probability of a customer waiting more than 3 minutes in the system before being served. Okay, waiting time. So in the system, so this particular one is going to be e to the power negative mu minus lambda times t. So t is going to be 3 minutes. All right, good. So this particular one is in the system. So I just intentionally brought the Q calculations to compare with the system, so that you know that anytime you have a question like this, you have to be very careful. Yes, be very careful. The latter is the correct answer. The first one is just for demonstration purposes. Okay, so our final answer is going to be 0.22313 as our final probability. Okay, let's look at the last question and we call it a lesson. We have to determine the idle time of the vendor clerk in a shift of 8 hours. Okay, in a shift of 8 hours. The idle time, we all know the idle time is going to be what? P naught. So P naught is 1 minus rho, which will be 0.2. Okay, yes. So 8 hours, which we know every hour is 60 minutes. So we multiply it by 60, we get 480 minutes. Okay, but the idle time per minute was 0.2. Okay, so when we have to multiply 480 by 0.2, and we get 96 minutes as our final answer. So thank you very much for being with me for this video. God bless you. See you in the next lesson. Thank you.